So, good morning and welcome to the 15th lecture. So, in this lecture, we will talk about examples on information capacity and mutual information. So, basically, we will be continuing our discussion from the previous lectures where we saw a few other examples on information capacity. So, today we will see both that's the information capacity as well as mutual information. So, let us begin our first example, that is need to prove here the information mutual information between x and y is equal to entropy of the input plus entropy of the output minus the mutual entropy between x and y, that is input and output. You need to establish this relation. So this is basically one of the properties of mutual information. So to prove this, we already know some of the uh, parameters as well as some of the relations between the mutual information. So in case of mutual information between x and y, this also can be represented by this equation. So that is nothing but probability between x and y. This is the mutual probability between x and y, log of conditional probability of input divided by the probability of input. So here we have two summations, one representing the input, that is all the input symbols emitted by the source, and the next one represents the output symbols. So based on this relation, so this is a well-known relation, we have visited this even in the previous lectures. So now in this equation, we can further simplify some of the terms. That is, we know that the conditional probability of input when you are very certain about the output, that's equal to the joint probability between x and y divided by the probability of the output. So this is also a well-known equation from the base equation. So now we try to replace this term in this equation. So since we have this conditional probability of input here, so that is nothing but the joint probability between input and output divided by the probability of output. So we will replace this term in this equation by this right hand side. So we will do that here. So basically now we will be merging this equation as well as this equation. That means we will be substituting this term by the equivalent term here. So how it looks like. So again, the mutual information between x and y is equal to these summations. One represents the input symbol, other represents the output symbol, because we need to compute the probabilities for all these input as well as output to find out maybe the joint probability or the uh, conditional probability. So here pxy, that is the joint probability between input and output, that's the same term here. It is rewritten here, log of, so this term here being replaced by this term. So that is nothing but joint probability between input and output divided by the probability of output multiplied by the probability of input. So this term is from here. Okay, now further what we can do. So if you observe the previous equation here, so we have a term log of a divided by b and another term c here. So this can be further simplified, that is, this is of the form log of a divided by b and c. So that is nothing but log of a minus these terms, log of, so log of b plus log of c. Since we have minus term here, that becomes minus log c. So this is the simple logarithmic equation, I mean relation, log of a by b, that is log of a minus log b. Okay, now we will use this relationship in the previous equation. Since we have observed that the previous equation has this kind of term, we will be representing that by this format. So similarly, we will be doing that here. The information, that's the mutual information between x and y, is equal to the first term. I will go back to the previous slide and show you first term and log of the a minus log of b minus log of c. That is, I just go back to show you here. So we have the first term as it is, and log of a, b, and c. That's what we are going to expand here. So this summation and joint probability between x and y. Then we have these terms. Even these terms have this summation. So those summation log of a minus those summations log of b minus summation log of c, and so on. So that's what is written here. So the first term and log of a minus the summation and log of the second term and third term is written here. This is c is written here. So basically we just applied this logarithmic relation to this basic equation here. This multiplied by this and this multiplied by this and this term multiplied by this term, where these terms are log of a minus log of b minus log of c, that form. Okay, now if you see the first term here, what do you remember by seeing the first term here? So the first term here, it consists of two summations and probability and log of probability. So this is of the general term of or general form of entropy, right? Entropy is nothing but probability log of probability. So here this leads to entropy, that's the joint entropy. Since the probability is a joint probability here, we get the entropy as a joint entropy here. So we have a minus term here because we need to have a minus term here when we write the entropy. Entropy is basically minus log of probability, minus probability log of probability. So since there is no minus sign here, it comes here. So that's minus of joint entropy. Next, for the second term, when you see here the second term, in the second term, if you consider only this summation and p of xi y yj, that is equal to p of xi, that's the probability of input. So can you realize this? Maybe in case if you consider the channel matrix, for example, a channel matrix may have two inputs, x1 and x2, and maybe two outputs, y1, y2, or more than two outputs, that's possible. So let us take two outputs here, y1 and y2. It is a simple case, y1, y2. Okay, we have some values here, some values here, some values here, as well as for x2 and y2, we have some values. So this is the transition probability from x1 to y1, and this is the transition probability from x1 to y2 here. Similarly, at this point we have the transition probability from x2 to y2, that is written here, and the transition probability between x2 and y2 is written here. Now if you see this term, the summation j is equal to 1 to m p, that's the joint probability between x and yj, is equal to pxi. Why? So in this case, what is varying? only j is varying, that is the column is varying, right? We are shifting from this column here to the next column here for a common row I. The row is common here, for example this row. That means when you find the summation of this value here as well as the value here, when you add up these two, what do we get? We get the probability of xi, right? That's the probability of xi. In this case is the probability of x1. So that is what we do here. We vary the column, the index j is varied. So here this column, or we go to the next column and find the summation here, right? So those summations will give us what? Give us the probability of x1. Probability of x1. Similarly, if we change to this these two items here, these two elements, then we should be getting the probability of x2. So this is the general equation that gives us the probability of input. So we can use the, so here we can use the second term when we have j varying from 1 to n, and joint probability between x and yj is nothing but probability of input pxi, because of this reason as mentioned here. So basically we will be changing in this summation, we will be changing the column. So here right now we are in this column, next we are going to this column for a fixed row. So then we will be adding these two items. So when we sum up this, we should be getting the probability of this element, that is this input xi. So in this case xi x1. Similarly, if you do this for the second row, which corresponds to the transition probability of the second input and the various outputs, when you change the column here, that is I'm talking about this summation here, when you change the column from here to here and you add up these two probabilities, then you should be getting the probability of x2. So in general, that is represented in this way. The joint probability between xi yj, when you vary or when you uh, add the probabilities for different column items, then you should be getting the probability of input itself, the corresponding input symbol. Okay, with this knowledge, this term can be represented as the probability of input. So this becomes summation I is equal to 1 to m pxi log of pxi. And then we will move on to see, can we further simplify the third term? So here, in the third term, here, so this is a simplification of the second term. So that is nothing but pi log pi. So that is nothing but the entropy of the input. Now we'll go to see the third term. The third term is what? Third term is p of xi yj. When you vary the row, that is equal to the probability of output. So is it the case? We can go back and or I can rewrite the same matrix here. So we have two elements at the input as well as output. That is, we have two input symbols x1 and x2, and we have two output symbols y1 and y2. Okay, now the transition probabilities are here. Any values here for x2 y1 and x2 y2, some values here. Now what is the condition here? We will be varying the rows for a constant column. That means we will be changing from this row to this row, for a constant column. Maybe the constant column is this column. And then we will be adding those probabilities. We add those probabilities. And what we get? We add this as well as this. So when we add these two items, we should be getting the probability of y1, right? Y1. So that is what written here, probability of yj. So this is in general, but for a specific case, addition of these values will give you the probability of y1, and addition of these values will give you the probability of y2. That is a specific case. So the equation is in a general form. That is, when you consider a constant column and you vary the row, you're varying the row from here to here for a constant column this, then you sum up these probabilities, you should be getting the probability of output. So that is what the general relation here is. So in the third term, we can rewrite that as probability of yj log of probability of yj. So that basically represents the entropy of the output. So right now we have simplified all the three terms. So the first term is nothing but the joint entropy between x and y. The second term is here the entropy of the input, and the third term is from here, that's the entropy of the output. So this is what is required. So hence this relationship is proved. That is, the mutual information between x and y is equal to entropy of the input plus entropy of the output minus the joint entropy between x and y. Okay, let us move on to the next example here. So in the next example, it's given that mutual information between x and y is equal to mutual probability log of condition probability of the input divided by the probability of input. So we need to establish this relation. So this is also from a property of mutual information. So we need to prove this. How can we prove this? We need to simplify some of the terms here. So can we write the conditional probability of output, that is probability of yj, when we are sure about xi, is equal to the mutual probability between input and output divided by the probability of input. So this is a well-known equation from the Bayes theorem or Bayes relation. So since we can have this term, we should be able to represent those terms in this part of the equation. So we will see how can we rewrite it. So right now we can write P of xi yj, that is the joint probability, is nothing but the probability of the input multiplied by the conditional probability of output. That's what's written here. Then we have the term summation j is equal to 1 to n. The joint probability between xi yj is nothing but p of xi, and the joint probability of yj, conditional probability of yj. So this is the conditional probability of yj. So basically it's nothing but the same equation, earlier equation, with the summations introduced here, because we want to simplify some of the terms. So here, for the same equation, we have introduced a summation term here, taking summation with respect to j on both the sides. So this can be further simplified as I mean, we have the left hand side here and the right hand side, if you observe carefully. So P of xi multiplied by this is summation conditional probability of yj xi. So here, because this is summation, this term is independent of j. There is no j term here, so this will not affect the summation here. I mean, summation is not affected by this term here. So this term can be written outside, and this summation applies only to this. As a result, we write it here. So P of xi, the same term which is here, is written here, and then we consider this summation for this term. That is what written here. So now if you observe P in the next step, we can further simplify this. That is P of xi, that is as it is here, and this term, entire term, is equal to 1. Why? Because if you see the conditional probability of output for any value of, I mean, known values of the input, and if you sum up them, that is, if you sum up the j represents the output or the column, then the total summation will give us 1. That is, the sum of the probabilities is equal to 1, right? So that is what written here. The total summation of all the probabilities for j, for all the j's, equal to 1. So basically this is the probability of the output. Total probability of the output will be equal to 1, or should be equal to 1. That's what written here. So with this, we can simplify this as probability of input. So right now we have summation j is equal to 1. The joint probability between input and output is nothing but the probability of input itself. So we also know that the mutual information between x and y is equal to the entropy of the input minus the conditional entropy of the input. Now, how can we rewrite this term? So mutual information between x and y is equal to, actually we will be expanding this entropy term, and we will be rewriting this entropy in terms of probability. So that is nothing but minus summation of pi log pi, that is for hx. We are substituting these terms for hx, and again we have a minus and minus and minus plus. So double summation here, that is for x and y, and we will be expanding this entropy, that is a conditional entropy, and rewriting it in the form of probability. So we know the conditional entropy of the input is equal to the joint probability of the input log of conditional probability of the input. So this is the general equation for conditional entropy. So that is what written here. Now refer the previously established relation for Pxi. So we know what is Pxi that we established earlier, and then we will substitute that in this, because we have a Pxi here. So what is Pxi? We earlier established. So Pxi is nothing but summation j is equal to 1 to n, and that's the joint probability between input and output. So that is what we will be substituting here. So since we have Pxi here, we will be replacing this Pxi by summation j is equal to 1 to n, joint probability xi yj, and log of Pxi. The same term continues here, plus this term. Okay, there is no change in this term. I mean we are writing this term same here. And then, do we have some common terms? Yes. So mutual information between x and y is equal to P xi yj, that is a common term, and log of this term minus log of the second term. So that is from the previous equation. So in this case, we had this term here as well as this term here common, which is a common term taken out, and then we will be left with minus log of pxi and log of conditional probability between input and output. So that is what is written here. So the one of the common term is taken out and log of conditional probability minus log of probability of the input. And this leads us to this term, that is pxi log of a by b, because we have the term here log of a minus log of b, that can be simplified as log of a by b. So this is what the final relation we need to establish. So mutual information between x and y is equal to this term. So we have established the relation here again. Okay, now let us move on to the third example. So in the third example, the question is find the rate of information transmission for the channel. So it is given that the probability of both the input symbols is equal to 0.5 and they are equal. Also, you need to assume that the rate of information or input information rate is equal to 10,000 symbols per second. So more specifically, a channel is given here. The channel consists of two symbols, input symbols x1 and x2. And at the output, you have three output points, y1, y2, and y3. So the transition probabilities are given here, like x1 to y1 is 3 by 4 and x1 to y2 is 1 by 4. Similarly, x2 to y2 is half and x2 to y3 is also half. So with this, we need to find the rate of information transmission for the channel, that is R, we need to find out. So we know the general equation, the rate of information is nothing but the product of entropy and the input rate. Okay, so with these given details, we need to find out that. Okay, we will start our computation here. So since we know the channel here and also the transition probability, the very first thing what we can do is to find the channel matrix. And we know these equations, that is mutual information between x and y is nothing but the entropy of the output minus the conditional entropy of the output. And right now, since we know the channel and the transition probabilities, we will move forward to write the channel matrix, that is condition probability of the output. It can be represented as this way. For example, x1 and x2 are the two symbols here, and at the output we have y1, y2, and y3. So x1 to y1 is 3 by 4. So here x1 to y1 is 3 by 4, and x1 to y2 is 1 by 4, and x1 to y3 there is nothing, so it's 0. Similarly, it is written here x1 to y2 is 1 by 4 and x1 to y3 is 0. Similarly for x2 to y2 is half and x2 to y3 is half, and the first one is 0. So x2 to y1 is 0. There is no connection from x2 to y1. So that's 0. And x2 to y2 is half. x2 to y3 is also half. This is the conditional probability of the output, or this is the channel matrix. Now, the joint probability matrix between x and y is equal to the condition probability of the output multiplied by the probability of the input. Since we know the probability of input, that is 0.5 and 0.5, it is given in the question, and we have right now found the channel matrix or the conditional probability of the output, we can directly compute the joint probability matrix between X and Y by computing the product of these two matrices. So this matrix we have already found, and this matrix is a row matrix consisting of two elements, that is 0.5 and 0.5. So that comes from these two terms, x1 and x2 are 0.5. So Px is a row matrix consisting of two elements, 0.5 and 0.5. So when we, as written here, and when we compute the product of these two matrices, we should be getting this value, that is the joint probability between X and Y is nothing but this. So this comes from multiplying this matrix by this. I can go back and show you here. So this element is multiplied by 0.5. So multiplying by 0.5 is like dividing by 2. So that becomes 3 by 8. This is 1 by 8 and so on. So that is what written here, 3 by 8, 1 by 8, and other terms 1 by 4, etc. So now the joint probability matrix, we can write probability of the output with the help of this. How to write that? The probability of the output is nothing but, if you see here, so this is the joint probability between X and Y. From this, we can deduce the probability of the output. So that is nothing but, you consider these columns here. So that is the probability of the output. So this we have seen in the first example. So here 3 by 8, and then here the sum of these two items or elements gives us the probability of y2, and then some of these items give us the probability of y3. So altogether that gives the probability of the output. So now from the probability we can find the entropy. Since in the previous step we found the probability of the output Py, now we can directly find the entropy of the output. So entropy is nothing but negative sign of with the probability of output log of probability of output. So when we substitute those values here, that is first value is 3 by 8, second value is also 3 by 8, and third value is 1 by 4, and we sum up all these, we should be getting the entropy of output. So that should come around 1.561 bits per symbol. Next, the conditional entropy of the output is equal to joint probability log of probability of output divided by input. So that can be written in this way. So this is basically from the previous term. So 3 by 8 we know, and we know also these values p of xi yj. This is what we found initially in the first step. And then we have log of probability of output divided by input. So that is what written here. So let me go back to show you that. That's the joint probability between x and y. P of xi, x and y. We have the term 3 by 8 here. And also we need to find y by x. So that gives us here. So that is what written at this point here. 3 by 8 by 2 gives us 3 by 4. Similarly, the second term, third term, and fourth term. We have only these four terms because the other two terms are, other remaining terms are zeros. So only these four terms, and that's 0.5. When you divide, you get those values here. That's what written here. And then entropy, that's the conditional entropy of the output, is this. That is basically the simplification of this. So we know these terms. These terms are, that is, probability of, joint probability between input and output is from the first step that we have found, and then we are dividing output by input, that is written here. So input is 0.5, the output is given in a matrix. Accordingly, we find that here. Okay, then after this, the mutual information between x and y is equal to entropy of the output minus the conditional entropy of the output. So we have already found this as well as this term. So we just need to substitute here to get the result. That's the mutual information between x and y. Now coming to the main part of the question, that is the rate of information transmission is given by this term, or this equation. This we have seen several times. So rate of information is equal to the mutual information multiplied by the input information rate. So we have the mutual information here that we substitute in this point, and the input information rate is given in the question, so that we substitute here to get this value. So this gives us the rate of information transmission. Okay, now we will discuss another key concept here, that is called as the Shannon's channel capacity. So Shannon and Hartley gave a theorem to find the channel capacity. So that theorem is as mentioned here. Consider a band-limited Gaussian channel operating in the presence of additive white Gaussian noise. So we have some information source that emits different symbols into the channel. Maybe as shown here, we have a channel here, and into this channel an information source emits different symbols. So when this information propagates through this channel, always some noise gets added here, and we get some output here that we Y. So the noise here added is En. So this is basically we'll have the Gaussian distribution. So that is called as additive white Gaussian noise. So we have the input symbol. When it propagates through the channel here, noise will be added, and that noise will influence the input, that is what we are going to transmit. As a result, at the output, we may get the same information, that is what we transmit, or we may get something else. So in this condition, if the channel is band limited, that means this channel has a finite bandwidth here. This channel has some finite bandwidth, that is called a band limited channel, and the noise that gets added will have a Gaussian distribution, that is called as Gaussian channel or white Gaussian noise. Then the theorem says that the Shannon-Hartley theorem for the channel coding states that the capacity of this channel is given by bandwidth and log of 1 plus signal to noise ratio. So here we need, in this context, we need to find out what's the amount of information the channel can carry. That is given by the channel capacity. So that is equal to the bandwidth of the channel, because we consider that this channel has got some finite bandwidth, log of 1 plus signal to noise ratio, because we will be transmitting some information here with some power, and in the channel some noise gets added. As a result of that, the output here, what we get, may be the same information that we transmitted, or may be different. Okay, whatever it may be, then what is the amount of information that we can carry through the channel? How can we measure it? That can be measured using this Shannon's channel capacity equation. This is a very popular equation in communication systems. It is called as Shannon's channel capacity equation. C is equal to B log of 1 plus signal to noise ratio. So C is the channel capacity that is computed as bits per second, maybe 1 kbps. What we say, a telephone line has a capacity, or when we transmit a wireless channel, we say it has 1 Mbps data rate. So that is what the capacity here, capacity of a channel. Since we know the bandwidth of the channel, we can find the channel capacity. And B is the bandwidth of the channel, and S by N, that's the signal to noise ratio. This is the signal power divided by the noise power. The signal power, what we introduce here to the channel, divided by the noise power, that is the noise gets added in to the channel. What's the power of that? So that ratio gives us SNR. So now we will solve an example to understand this concept more in detail. For an AWGN channel with the 4 kHz bandwidth and the noise for spectral density, the spectral density of the noise is given here. That is represented as NO by 2. So that is equal to 10 power minus 4 lag per hertz. The signal power required at the receiver is 0.1 milliwatt. So then, in this context, calculate the capacity of the channel. So how can we solve this? So right now, in the question, what information is given? So the first information given is the bandwidth. The second information is given is the noise power spectral density. Some information regarding noise power is given here. And another information given is the signal power required at the receiver. Signal power is also given. We need to find out the channel capacity. So channel capacity is C is equal to B log of 1 plus signal to noise ratio. So it seems like we have most of the information required to find out the channel capacity, but we will see that. So right now we have the bandwidth and also the signal power given here, but we need to know more about noise because we need to find out the signal to noise ratio. So noise is nothing but the bandwidth multiplied by the power spectral density. Yes, noise power spectral density N naught. But here NO divided by 2 is equal to 10 power minus 11. But we need NO. Since if the noise power is directly given, then we can substitute that. But in this case, the noise power spectral density is given. So in that case, to find out the noise power, that is equal to bandwidth multiplied by the spectral density. We know here NO divided by 2. So NO, which is required to substitute in this equation, is equal to 2 times the value here, right? Because half of that is 10 power minus 12. So NO is 2 times of this. So that is what substituted here, multiplied by the bandwidth. Bandwidth is 4 kilohertz, that is substituted here. So that gives us N. So that value, when we multiply, we should be getting here. And we have the equation for channel capacity. So C is equal to B log of 1 plus signal to noise ratio. So this is the equation for channel capacity. So when we substitute the values in the above equation, that is, since we know all those values, we can find out the channel capacity as so many bits per second. And then Now we'll move on to the next example, a more detailed example. It is given that a CRT terminal which is used to enter the alphanumeric data into a computer. So CRT is connected through a wall-squared line of bandwidth 3 kHz and the SNR is 10 dB. Now you assume that the terminal has 128 characters and the data is sent in an independent manner with equal probability. In this context, find the average information per character, find the capacity of the channel, and also find the maximum rate at which data can be sent from the terminal to the computer without error. So how can we find out these parameters? So first we need to find out what details are given in the question. One is signal to noise ratio is given. It is given in dB. Generally, signal to noise ratio is a number because there is no unit associated with the signal to noise ratio. It's a normalized value, normal value. For example, signal is a power, noise is also power. So when you find the ratio, it becomes unitless. But it is given as in dB, so we need to convert into normal value. Okay, so one data given here is signal to noise ratio, and another input given here is the bandwidth, and also the information given here is like 28 characters are input into the system, and they have the equal probability. So let us try to find out all these parameters from the given details. The first step, we know how many symbols are emitted into the channel, 128 symbols. So can we find out the entropy? Because all those symbols are equally probable. So we know when the probabilities are equal how to find out the entropy. So that is nothing but log of n. That is log of 128 characters base 2. So that's equal to 7 bits per character. So since the probabilities are equal, we get the maximum entropy that is equal to 7 bits per character. So now signal to noise ratio is given as 10 dB. So that is equal to 10 log of signal to noise ratio. So that is equal to 10 dB, that's a given. So we need to find out what is the value of signal to noise ratio in a normal scale. So please note here, this log is base 10 because we are talking about dB here. So 10 log of some value here will give us 10 dB. What is that? So S signal to noise ratio is 10, right? That means log of 10 to the base 10, that is 1. 1 multiplied by 10 gives us 10. So signal to noise ratio in normal scale is 10. So basically we are converting from dB to normal. So its signal to noise ratio is given as 10 dB. So when you convert it into normal, it becomes 10. Okay, with that we can find out the channel capacity C is equal to B into log of 1 plus signal to noise ratio. So we know signal to noise ratio here, and also we know the bandwidth, then we can find out the channel capacity. And then finally, we substitute and get the values here. And then the average rate of information R is nothing but R multiplied by entropy. We have found the entropy in the previous slide, and this value is we need to find out.